Have you ever pondered why all things in the cosmos rotate, yet we perceive ourselves as entirely motionless? Our planet rotates below us at more than 1,000 miles per hour. The Earth revolves around the Sun concurrently. Our whole solar system journeys through the galaxy at almost 500,000 miles per hour. Despite this, no vibrations are felt. Your respiration stays constant. The atmosphere doesn't tug at your epidermis. It appears as though we are static within a dynamic cosmos. However, what if this perceived immobility is merely a deception? Suppose movement is so profound and unceasing that our sensory organs merely yield to it. This evening, we delve into that enigma, seeking to understand not only the reasons for motion but also why cessation of movement is impossible. Should you be prepared, please press the like button, and together we shall uncover a revelation that will permanently alter your perception of the universe. At this very moment, while you hear these utterances, the globe is rotating under your feet at over 1,000 miles per hour. You are traveling at a speed exceeding that of a jet, surpassing any tempest ever documented. Concurrently, the world is hurtling around the sun at almost 67,000 miles per hour, charting an unseen trajectory through the void. Furthermore, our complete solar system is orbiting the core of the Milky Way at nearly 500,000 miles per hour. This represents multiple strata of movement arranged like rotating cogs within a timepiece vastly grander than one can conceive. Nevertheless, you perceive no sensation. Your physique remains tranquil. The atmosphere surrounding you does not stream by. The ground underfoot neither shakes nor inclines. A container of water rests without agitation. The celestial bodies seem stationary. It's as though the cosmos itself has opted for immobility, yet this is among the most profound deceptions. Our existence unfolds within a reality where constant movement prevails, though the reasons for it remain largely incomprehensible. We must abandon the notion that movement invariably makes itself evident. When movement is fluid and consistent, it becomes imperceptible to our sensory organs. Our perception isn't of velocity itself, but rather of alteration, an abrupt transition, a propulsion, a traction, a disparity from one instant to the subsequent. As an automobile gains speed, your torso reclines. Upon deceleration, you are propelled ahead. However, once the vehicle attains a constant velocity, the feeling diminishes. Traveling at 60 miles per hour on an unswerving road, one could poise a coin on the instrument panel. The movement has not ceased, rather your perception of it has. The Earth's planetary spin operates identically. It is age-old, consistent, and continuous. There exists no initial juncture. You cannot recall any instance when the globe abruptly commenced its movement. Each atom within your being, every inhalation of atmosphere, every particle of sand has been in collective motion for eons. You are not merely traversing the Earth. You constitute a component of it. This exemplifies the subtle force of inertia. Once an object is in motion, it will persist in that state unless an external force compels a modification. The Earth rotates, not due to perpetual propulsion, but because no impediment halts its progress. The vacuum of space provides virtually no opposition, no abrasive force, no celestial braking mechanisms. Movement, once initiated, merely endures. The vestibular system within your ear, which confers equilibrium. It was never engineered to detect the Earth's rotational movement. It developed to aid our ancestors in walking, climbing, and avoiding falls. It detects changes in speed, not constant velocity. That's why you sense turbulence on an aircraft, but not its steady cruising. The Earth's rotation is so smooth and consistent that it never registers with your senses. To your physical self, it feels like complete rest. Astronauts encounter this deceptive perception on an even grander scale. Inside the International Space Station, they journey around our planet at nearly 17,500 miles per hour, completing an orbital path every 90 minutes. From an external viewpoint, it represents one of the swiftest movements ever accomplished by humans. Internally, however, it feels serene. Objects gently float. There is no awareness of velocity, only an absence of weight. Movement without any resistance is perceived as stillness. Even the surrounding air contributes to maintaining this illusion. The atmosphere revolves with the planet, held fast to Earth by gravity. If the terrain beneath you were spinning while the air remained stationary, the resulting winds would be catastrophic, shrieking across the surface at supersonic speeds. But this does not occur. The air, the oceans, the land, and your body all progress together, sharing the identical rotational rhythm. To perceive motion, you require a contrast. You need something that refuses to move alongside you. A straightforward experiment exists that uncovers this concealed rotation without needing to leave the ground. Suspend a lengthy, heavy pendulum so it can swing freely in any direction. Allow it to oscillate back and forth, uninfluenced by motors or guides. Over time, the trajectory of the swing appears to pivot. The pendulum seems to gradually alter its orientation, even though nothing is pushing it sideways. What is truly happening is more subtle and profound. The pendulum maintains its original direction, while the Earth rotates beneath it. The ground revolves, the pendulum remembers. This quiet disparity between them reveals the planet's movement, one slow degree at a time. It is not dramatic, it is patient, and it is undeniable. This observation highlights something crucial about the cosmos. Movement does not have to be loud. Often, the most powerful forms of motion are the quietest. Earth's rotation establishes day and night, influences weather patterns, and helps generate the magnetic field that shields life from cosmic radiation. Yet it achieves all of this without producing vibrational sound, akin to a massive engine humming below the threshold of perception. On a deeper level, this deceptive sense of stillness hints at a fundamental truth regarding motion itself. Absolute rest does not exist. Everything moves relative to something else. From your perspective, you are stationary, and the stars move. From another perspective, the stars are motionless, and you are the one rotating. Physics makes no distinction between these two scenarios. Motion is dependent on the frame from which you observe it. This explains why the universe can be endlessly dynamic, yet convey a sense of tranquility from within. You are not observing motion from an external vantage point. You are embedded within it. Like a leaf drifting in a slow river, you do not feel the current unless you brush against the shore. If the Earth were to suddenly stop spinning, the illusion would instantly shatter. Oceans would surge across continents, and powerful winds would tear through the atmosphere. The ground would no longer synchronize with the movement of the air or the water. That intense disparity is what we associate with the sensation of motion. Its lack of perceptible movement doesn't indicate immobility. Rather, it signifies an exceptional state of equilibrium. This rotational movement even influences the very nature of time. Our daily cycles, our calendrical systems, and our perception of rhythm all stem from the Earth's revolution. We remain unaware of it, as it forms the fundamental backdrop of our lives. It functions as an unheard metronome, its rhythm ingrained in us from birth. Therefore, when you perceive yourself as stationary, you are not separate from movement. Instead, you are enveloped within one of the most fluid and enduring motions the cosmos has ever generated. This movement is so ancient and ceaseless that your sensory perception interprets it as tranquility. Furthermore, this merely marks the initial stage. Since we don't perceive the Earth's rotation, despite knowing it occurs, a more profound inquiry arises. If all things move with such inherent ease and spontaneity, what was the original source of that motion? To comprehend the universal phenomenon of spin, we must journey backward, not merely through historical epochs, but through the very fabric of existence. Beyond the emergence of societies, the Earth's genesis, the sun's ignition, and even the earliest stars. Our journey must extend to an era preceding any discernible structure, before light could propagate unimpeded, and before the cosmos mastered expansion without self-destruction. We must revert to the Genesis, to a point where the fundamental concept of movement was being inscribed into being during the universe's initial infinitesimal moments. No void existed, awaiting occupation. Space itself was actively coming into existence. Time wasn't merely progressing in the background. It was developing concurrently with space, intrinsically linked. All future existence was compacted into a condition of such extreme heat and density that contemporary physical laws find it challenging to characterize. Nevertheless, even amidst that profound simplicity, the cosmos lacked absolute equilibrium. Utter balance implies an absence of activity. A cosmos possessing complete symmetry would lack any impetus for alteration. No particular orientation would be preferred. No formations would materialize. It would persist as seamless, homogeneous, and everlasting. However, the cosmos we occupy differs from that hypothetical one. It bears the marks of incompleteness. Minute variations in energy and density served as initial strokes upon what was otherwise a pristine canvas. These flaws manifested as quantum instabilities. Even within the most absolute vacuum, quantum fields are perpetually active. They constantly waver and vibrate, momentarily acquiring energy before releasing it. In the nascent cosmos, such variations were inevitable, and as the universe expanded, these minute tremors were elongated across vast distances, embedding them into the very structure of space. A portion of these initial variations possessed angular momentum, which is the fundamental component of rotation. This concept is vital. Spinning does not necessitate an outside force to initiate it. It merely requires an asymmetry, a minor disparity, a subtle bias towards one orientation versus another. As soon as such a bias manifests, the principles of physics guarantee that movement will ensue. With the universe's cooling, the initial particles came into being. Quarks coalesced to form protons and neutrons, electrons appeared, and subsequently combined with nuclei to create atoms. These developments did not occur independently. Matter aggregated within a cosmos already imbued with movement, already containing subtle directional inclinations inherited from its very genesis. Subsequently, gravity assumed control. It collected material into immense nebulae of gas and particulate matter. These clouds weren't entirely motionless. They acquired the subtle rotational forces ingrained within the universe's framework. Their rotation intensified as gravitational forces drew them inward. This identical principle holds true across all of nature. When matter condenses, its spin quickens, akin to a skater retracting their arms. The cloud's angular momentum became more focused. Stars emerged, rotating, and around these nascent stars, residual material flattened into spinning disks, eventually forming planets, moons, and rings. Whole solar systems materialized as enduring vortices of ancient motion. The spin didn't need to be restarted, it was already present, amplified by collapse and maintained by inertia. On grander scales, galaxies develop in the same fashion. Vast regions of matter collapsed under gravity, acquiring their rotation from the surrounding cosmic environment. As they condensed, they began to rotate, arranging themselves into spinning disks and spirals. These are the graceful arms we observe in galaxies today. Are not arbitrary embellishments. Instead, they are records of motion solidified into shape. Some scientists have pondered whether the universe itself might exhibit a subtle, overarching rotation. Not a dramatic rotation like a top, but a faint, large-scale twist within space-time. When researchers examine the oldest light in existence, the cosmic background glow remaining from the universe's earliest era, they find it is remarkably uniform, yet not entirely perfect. Minute alignments and directional patterns emerge, suggesting the universe may have possessed a slight orientation from its inception. If such a global rotation exists, it would be extraordinarily small, far beyond typical human experience. Yet, even a minuscule twist, present at the outset, could have been amplified by cosmic expansion, leaving its imprints on galaxies billions of years later. Whether the universe as a whole rotates remains an unresolved question. What is evident is that rotation manifests universally once gravity and time are allowed to interact. At its most fundamental level, spin is not something added to matter later. It is intrinsic. Every known particle possesses intrinsic spin as an integral part of its identity. This is not literal rotation in space, but an inherent angular momentum that determines how particles interact, bond, and obey the rules of nature. Without this intrinsic spin, atoms would not form stable structures, chemistry would fail, matter itself would behave differently. This implies something profound. Rotation is not a characteristic layered upon the universe. It is an integral part of its foundation. Nothing in the universe begins to spin from nothing. Every rotation can be traced backward through a chain of lineage. A planet spins because its progenitor disk was spinning. That disk rotated because the cloud that formed it was spinning. That cloud, in turn, spun due to motions embedded within the early universe. And those motions trace back to the initial broken symmetries at the dawn of time. So who initiated the universe's spin? Physics provides a quiet, almost unsettling answer. No one did. The universe did not require an initial push. It did not require an external cause to initiate movement. Motion emerged naturally once perfect symmetry could no longer be maintained. And once motion came into existence, it could never be eradicated. Only redistributed angular momentum is conserved. It's indestructible. It can be moved, distributed, weakened, or intensified, yet it persists. Across eons, rotational speed decreases in some areas and accelerates in others. Planets progressively diminish their rotation, whereas moons acquire orbital energy. Stars release angular momentum into the cosmos. Galaxies swap it during impacts, yet the overall quantity is never lost. Such preservation endows the cosmos with a form of recollection. Each rotation observed now represents a continuation of movement present well before stars began to shine or planets solidified. Movement embodies the preservation of history through rotation. The very concept of time appears connected to this principle. Our measurement of time relies on cycles, daily, yearly, oscillations, and recurrences. All these cycles originate from movement. Lacking movement, time would lack its indicators. The initial rotations of the universe might have contributed to establishing not only its structure, but also the fundamental tempo by which alterations are gauged. In this context, the cosmos did not commence in a static state, only to later initiate movement. It originated already in flux, already asymmetrical, already incapable of maintaining absolute equilibrium. This inherent dynamism proved to be foundational, as that initial disequilibrium gave rise to rotation, which in turn produced structure, leading to stars, planets, chemistry, and ultimately life. The rotational motion propelling galaxies now is not a novel occurrence. It is a reverberation mellowed by the passage of time, expanded by the vastness of space, yet never extinguished. This leads us to the subsequent phase of our narrative. Assuming rotation existed from the outset and influences the formation of stars and galaxies, what occurs when this rotational force manifests on the scale of a world capable of sustaining life? Might the mere act of rotation distinguish a lifeless planet from one teeming with life? To address this, we journey back to Earth and investigate how its spin evolved into the subtle driving force of existence. Picture Earth devoid of rotation. Rather than being entirely motionless, one hemisphere of the planet would eternally confront the sun, scorching beneath unceasing illumination. Its opposing hemisphere would remain perpetually dark, trapped in an unending night, experiencing temperatures far lower than any recorded in Antarctica. A constricted zone of twilight would separate these extremes, afflicted by fierce gales as heated air surged towards colder regions. This would be a planet of stark contrasts where equilibrium would be unsustainable. Oceans would become motionless, atmospheres would disintegrate, and the weather patterns we recognize would cease to exist. Life would never commence. The Earth's rotation is more than mere movement. It functions as a regulator and a distributor. It acts as a subtle designer, taking the sun's raw energy and disseminating it across the globe over time. Lacking this rotational movement, solar radiation would reach the surface inconsistently and remain trapped. The Earth's spin converts solar radiation into a rhythmic pattern. The most apparent outcome of this is the cycle of day and night. With Earth's rotation, each location on its surface alternately faces the sun and then turns away. This cyclical change prevents both uncontrolled heating and excessive freezing. This enables temperatures to vary within limits conducive to survival, establishing gradients sufficiently mild for chemical processes to endure. While life does not flourish in perfect stasis, it also cannot withstand utter disorder. Rotation positions Earth precisely within the confined range between these two extremes, yet the impact of its spin extends beyond mere illumination and shadow. As our planet revolves, various latitudes travel at differing velocities. Close to the equator, the surface moves more rapidly than it does closer to the poles. This velocity disparity causes moving air and water to curve, altering their trajectories instead of allowing them to proceed in a straight line. This leads to a worldwide circulation pattern influencing winds, storms, and ocean flows. While this curving phenomenon is slight, its impacts are immense. It structures the atmosphere into extensive systems, moving warmth from the equator to the poles and returning colder air. Lacking this movement, warmth would accumulate in one area and dissipate from another. The climate would break down into distinct extremes. Conversely, planetary rotation establishes a breathing-like rhythm, transferring energy much like blood carries oxygen throughout an organism. The oceans behave similarly. With Earth's rotation, ocean currents bend, creating extensive circular routes that transport heated water to colder areas and bring cooler water back towards the equator. Over vast geological periods, these currents maintain climate stability. They moderate temperature fluctuations and foster stable conditions, allowing ecosystems to endure sufficiently to develop intricate forms. The planet's spin also influences the atmosphere's density and characteristics. A rotating world retains its atmospheric gases more efficiently due to air circulation. It spreads out pressure and temperature, stopping the atmosphere from gathering in a single spot or completely dissipating. Planets with very slow rotation or diminished internal movement frequently lose their air, gradually eroded by solar radiation. Earth's rotation is also crucial far beneath the surface, in an area inaccessible to any life form. Deep within the crust, the core contains an immense sea of liquid metal. With the planet's rotation, heat dissipates unevenly from its interior, powering convection currents within this molten iron. In conjunction with the spin, these currents produce a magnetic field reaching deep into space. This field diverts charged solar particles, safeguarding the atmosphere and surface from continuous degradation. Lacking this magnetic protection, Earth's oceans would gradually vaporize into space. The atmosphere would become thinner, and radiation would relentlessly strike the surface. Mars serves as a warning illustration. Formerly warmer and more humid, it lost significant internal movement early on. Its magnetic field diminished, and the solar wind eroded its atmosphere. All that's left is a frigid, arid planet. In this context, rotation, seemingly halted, isn't solely about surface characteristics. It concerns the very existence of the planet. The speed of its spin is also significant. Should Earth rotate considerably quicker, days would shorten, winds would intensify, and storms would become more severe. If it rotated much slower, the temperature variations between day and night would increase, putting strain on ecosystems. Earth's present rotational speed isn't arbitrarily selected, but it exists within a limited range, allowing for sustained stability. Life emerged within this range and adapted so profoundly that it embodies the planet's rotation internally. All living organisms on Earth function according to an internal timepiece aligned with the daily cycle's duration. These circadian cycles govern sleep, metabolic processes, development, and conduct. These are not acquired behaviors. Rather, they are ingrained biologically at the cellular tier. Even organisms composed of a single cell monitor the progression of day and night. This inherent timing enables life to foresee alterations instead of merely responding to them. Plants get ready for dawn before sunlight appears, and animals modify their bodily functions prior to temperature variations. The planet's spin renders the environment foreseeable, and this foreseeability permits evolution to construct intricacy rather than simply enduring disorder. Furthermore, rotation maintains Earth's stable alignment in space. Our world's axis is inclined, leading to the occurrence of seasons, yet it maintains a steady orientation. This steadiness is partly attributable to the gravitational bond between Earth and its moon. This connection is established through the planet's rotation and its orbital movement. Without this stabilizing influence, Earth's climatic conditions could fluctuate dramatically over brief periods. Such instability might repeatedly halt evolutionary advancement. The moon itself came into being as a result of rotational forces. During Earth's early stages, a colossal impact imparted immense angular momentum to the system. The resulting fragments coalesced to form the moon, and the Earth-Moon duo gradually established a gravitational ballet spanning eons. This interplay has progressively decelerated Earth's rotation, extending the duration of days and tempering tidal movements. Life forms adjusted to these shifts, developing as the rotational speed subtly altered. Ocean tides also result from the planet's rotation engaging with gravitational forces. With Earth spinning under the Moon's gravitational influence, the seas predictably ebb and flow. These tidal movements might have been vital for nascent life, forming shallow basins that periodically filled with water and then receded. These conditions facilitate the concentration of chemical substances, foster intricate reactions, and offer pathways for the progression from basic molecules to biological entities. While rotation didn't directly generate life, it established the necessary prerequisites for it. This represents a state of equilibrium without inertia and transformation without disintegration. When researchers seek extraterrestrial life, they identify planets situated at an optimal distance from their host stars, but they also search for indications of planetary spin. A world that either lacks rotation or rotates too sluggishly is improbable to sustain a consistent atmosphere or climate. Conversely, a planet spinning excessively rapidly might be perpetually engulfed in storms. Planetary rotation contributes to habitability, even on celestial bodies vastly unlike Earth. This rotational motion influences various phenomena. For instance, gas giants rotate swiftly, producing potent magnetic fields and vibrant atmospheres. Frozen moons spin and revolve in manners that produce internal warmth via tidal friction, maintaining liquid oceans beneath their icy exteriors. Movement establishes energy differences, and these energy differences are fundamental to life. Across all magnitudes, living organisms appear to necessitate a cosmos that is perpetually in motion. This implies a nuanced yet significant truth. Life doesn't just coexist with movement, it fundamentally relies upon it. Inactivity leads to barrenness. Absolute equilibrium signifies an absence of life. Biological systems thrive away from perfect balance, continuously exchanging energy with their environment. The planet's spin is among nature's most dependable methods for sustaining this disequilibrium without compromising structural integrity. Earth rotates, and its rotation allows it to function dynamically. Air currents move, seas undulate, magnetic fields pulsate, and days unfold. Seasons transition, time acquires depth, and amidst this constant turning, chemical processes discovered opportunities for innovation. Molecules formed and reformed connections, cells came into existence, and ecosystems developed in successive layers. Ultimately, awareness manifested, conveyed by neural firings and cyclical rhythms, mirroring the planet's inherent patterns. Therefore, did planetary rotation enable life, not through mere coincidence, nor as an incidental outcome. The planet's spin generated the dynamic equilibrium essential for life. It kept Earth from solidifying into uniformity or erupting into disorder. It provided a direction for energy and a progression for time. Upon its emergence, life became intrinsically linked to that cadence, integrating the planet's rotational motion into its very biological makeup. This prompts a more profound inquiry. If rotation influences environments and biological systems so significantly, does its impact extend beyond climate and chemistry to something even more foundational? If rotational motion organizes matter and life, might it also influence time itself? This query directs us to the frontiers of physics, where rotation doesn't merely shift celestial bodies, but starts to warp existence itself. On ordinary scales, spinning appears innocuous. Our planet rotates silently, timepieces function as expected, and causality unfolds predictably. However, the cosmos extends beyond these familiar dimensions. Should rotation reach an extreme, with mass spinning sufficiently rapidly and densely, it transcends mere movement to become a deformation. At this juncture, rotation ceases to influence solely space and starts to mold time. This concept originates from a profound realization in contemporary physics. Space and time are not distinct entities. Instead, they are intrinsically linked within a unified framework, commonly termed space-time. The presence of mass and energy dictates space-time's curvature, and this curvature, in turn, governs the motion of matter. Rather than a distant attractive force, gravity represents the geometry of space-time reacting to mass. Nevertheless, gravity constitutes only a segment of the complete narrative. Movement also holds significance. An object that rotates doesn't simply reside within space-time. Space-time is pulled along by the object's motion. While this phenomenon is faint when associated with smaller bodies, it is verifiable and has been quantified. This phenomenon is termed frame dragging by physicists. It implies that rotational motion possesses the capacity to subtly distort the fundamental structure of reality, thereby marginally modifying the local behavior of space and time. Envision space-time as a dense, imperceptible fluid. A stationary object introduced into it merely causes a depression, whereas a spinning object agitates the fluid, generating a vortex. Any proximate entity is drawn into that rotational motion, compelled to spin irrespective of its inclination. Even photons are influenced. This description is not merely figurative. Empirical tests have validated this. As Earth rotates, it pulls a minute quantity of space-time along with it. This phenomenon is exceedingly minute, yet it can be quantified using highly accurate instruments. Orbiting spacecraft outfitted with exceptionally sensitive gyroscopes have successfully identified this distortion. The alignment of these satellites changes over time, not due to the spacecraft's own rotation, but because the space-time they traverse is subtly warped by the Earth's rotational motion. This reveals a remarkable implication. Time itself progresses marginally differently in the vicinity of a rotating celestial object. An increase in rotational speed and gravitational intensity amplifies the effect. While the distortion around our planet is moderate, it becomes exceptionally significant near more extreme celestial bodies. Let's examine a neutron star. Upon a massive star depleting its nuclear fuel, its core is so intensely compressed by gravity that atomic structures disintegrate. Protons and electrons combine to form neutrons, resulting in an object merely the size of a metropolis, yet possessing a mass greater than our Sun, all to preserve angular momentum. This compressed stellar core rotates at an astonishing velocity, occasionally completing hundreds of revolutions each second. These rapidly spinning remnants are known as pulsars. From their magnetic poles, these objects project beams of radiation, and their rotation causes these beams to traverse space akin to celestial beacons. When viewed from Earth, we detect exact pulses that recur with remarkable consistency. However, in the vicinity of a pulsar, space-time undergoes extreme deformation. The passage of time decelerates and trajectories become curved. Timekeeping devices positioned nearer to the surface register a distinctly slower rate compared to those situated at a greater distance. The powerful rotational force warps space-time with such intensity that even light finds it challenging to travel in linear paths. Progressing even further, rotation attains its ultimate manifestation, a spinning black hole. Such a black hole arises when gravitational forces overcome all opposing resistance, causing matter to collapse irrevocably past a critical threshold. When a black hole rotates, which is common, the warping of space-time intensifies to such a degree that space itself is compelled to spin. Close to a spinning black hole, an area exists where no object can stay motionless. Neither particles, nor light, nor even space-time itself can resist. All elements are pulled along in the rotational direction. Within this zone, the concept of immobility becomes irrelevant. Movement is compulsory. For a distant observer, time exhibits peculiar behavior in this vicinity. Items descending towards the black hole seem to decelerate, with their internal timekeeping mechanisms progressively slowing. Close to the spinning center, time undergoes dilation. Occurrences transpire dissimilarly based on your location and velocity. One observer's future might coincide with another's present moment. This phenomenon is not a product of speculative fiction. Rather, it's a direct outcome of the interplay between rotation and gravitational forces within the mathematical frameworks defining space-time. Even at considerable distances from black holes, we observe this phenomenon in our everyday existence. Unbeknownst to us, satellites circling Earth perceive time distinctly from terrestrial timepieces. Due to their rapid movement and elevated position within Earth's gravitational pull, their timekeeping devices operate at an accelerated pace. Positional guidance systems are required to continuously adjust for this discrepancy. Should the relativistic time warping induced by movement and gravity be ignored, contemporary technology would cease to function. Rotational effects are already influencing your perception of the current moment. This uncovers a vital insight. Time lacks universality. No singular, omnipresent cosmic timepiece exists that operates at an identical pace across all locations. The progression of time varies according to movement and gravitational forces. Given that rotation constitutes a type of motion, it directly impacts the manner in which time progresses. Under extreme conditions, this relationship grows even more peculiar. The mathematical formulas characterizing spinning spacetime permit outcomes where trajectories curve back upon themselves. These are self-contained temporal sequences where causality becomes indistinct. The actual existence of such trajectories is still unknown, yet the mathematical framework itself demonstrates the profound extent to which rotation can intertwine with time. Even photons retain a memory of rotation. Electromagnetic radiation traversing close to colossal rotating bodies experiences deflection and retardation. Light can be temporarily captured in an orbital path, circling before breaking free. Observers of the cosmos detect light reverberations close to spinning black holes, experiencing delays ranging from mere fractions of a second to several hours, contingent on its trajectory. These postponements are not coincidental occurrences. They represent time itself undergoing elongation due to rotational forces. At the vast scale of the cosmos, researchers have pondered if rotation might affect the universe's general temporal orientation. Although present data indicates the universe is predominantly uniform, exhibiting consistent behavior in every direction, certain inquiries persist. Faint configurations within primordial radiation suggest that the nascent universe might have possessed favored alignments, however subtle. If this holds true, rotation could have contributed to establishing not just its structure, but also the very directionality of time. The explanation for our perception of time progressing forwards instead of in reverse. The temporal arrow is intrinsically linked to entropy, which is the inclination of systems to transition from an organized state to a chaotic one. However, entropy necessitates operations, engagements, and movement. Rotation generates enduring formations, capable of retaining and transmitting energy. It postpones a state of balance. It enables intricacy to endure. From this perspective, rotation doesn't just distort time within a localized area. It might contribute to maintaining time as a concept with any significance whatsoever. Should rotation be absent, matter either rapidly collapses or disperses. Systems attain a state of balance and cease their transformations. When rotation is present, structures endure, variations remain, and time maintains its directionality and character. The universe's ongoing expansion even engages with rotational forces. With the expansion of space, angular momentum diffuses, yet it never disappears. Instead, it gets reallocated across increasingly vast dimensions. Movement grows more attenuated, sluggish, and dispersed, but its essence stays embedded within the fabric of space-time. This implies a profound concept. The universe does not merely traverse time. Rather, time is an entity that the universe itself produces via movement. Rotational movement imparts rhythm to time. Orbital paths establish cycles, while spinning motions generate recurrence. Recurrence leads to measurement. Measurement, in turn, establishes duration. If motion is absent, time's indicators disappear. If rotation is removed, time lacks any distinguishing characteristics. Currently, your perception of time is tied to the Earth's rotation. Atomic vibrations serve to define seconds. Days are determined by planetary rotation and years by orbital movement at all magnitudes. Time's passage is quantified by objects in motion. Indeed, rotation possesses the ability to distort time. It can decelerate, extend, contort, and reconfigure its progression. On subtle scales, this impact is imperceptible. On extreme scales, it fundamentally alters reality. This leads us to an even more profound enigma. Given that rotation influences time and time dictates change, what then dictates the evolution of rotation itself? What factors maintain spins consistently for eons or gradually diminish them? Should spin affect time, then what entity or force regulates spin? This inquiry draws us further into the concealed principles that dictate movement itself. If rotational forces are capable of distorting time, decelerating chronometers, and shaping the sequence of occurrences, then a more profound query naturally arises. What dictates the velocity at which an object rotates? What determines if a planet rotates steadily for billions of years or if a star spins itself into a much more unusual state? If rotational motion influences reality, what then controls the spin itself? Initially, one might be inclined to envision an unseen orchestrator, a celestial hand manipulating controls, accelerating elements in one place, decelerating them in another, yet the cosmos operates with much less overt intervention. It doesn't direct movement by decree, instead it governs it through equilibrium. The fundamental concept is angular momentum. This stands as one of the most rigorously preserved quantities throughout physics, distinct from energy, which can transform or matter. While matter can be generated or annihilated under specific circumstances, angular momentum proves unyielding. Within a self-contained system, it is incapable of disappearing. It invariably has to relocate. This solitary principle clarifies why rotational motion endures throughout the cosmos and why its alterations occur with such exact, foreseeable patterns. Envision a contracting gas cloud in the process of star formation. When gravity draws the matter inward, the cloud contracts. Were no other forces at play, it would directly collapse into its core. However, since the cloud possesses even a minuscule lateral movement, this motion intensifies as the cloud condenses. With the identical quantity of angular momentum confined to a reduced area, its rotational speed increases. This isn't a deliberate act, rather, it's an outcome. The cosmos doesn't determine an object's rotational velocity, instead, spin naturally adapts to uphold equilibrium. This equilibrium dictates everything, from subatomic particles to vast galaxies. A planet, upon its formation, acquires its rotation from the surrounding disk of matter orbiting its parent star. A moon, when it comes into being, receives its rotational motion from its planet. Similarly, when a star undergoes collapse into a compact remnant, its rate of rotation significantly quickens. No external interference is required. The governing principles manage this. Yet conservation should not be mistaken for unchangeability. Rotational energy is mobile. It can be exchanged. Should two entities engage through gravity, angular momentum is capable of moving from one to the other. This mechanism accounts for how rotational speeds evolve through time. A planet that is spinning can shed some of its rotation as its accompanying moon acquires orbital energy. A star that is rotating can release angular momentum into the adjacent cosmos via stellar winds. Furthermore, a galaxy might impart its spin to another galaxy during a gradual, elegant merging process. Our planet, Earth, offers a distinct illustration. Its rotational speed is progressively diminishing. Days are extending, not by significant increments like minutes or seconds, but by minuscule portions of a second across many centuries. The underlying reason is the tidal engagement with the moon. The Earth's spin causes the oceans to be pulled a little in front of the moon's location. The gravitational force of the moon then exerts a backward pull on these oceanic bulges, functioning as a retarding force. The rotational energy that is shed doesn't vanish. Instead, it is conveyed to the moon's orbital path, resulting in the moon gradually moving further away. Spin isn't eradicated, it's merely reallocated. This continuous interchange bestows upon the cosmos an extraordinary steadiness. While systems undergo evolution, they do not disintegrate. Rotational velocity fluctuates, yet it seldom ceases completely. Even in the presence of friction, it simply relocates angular momentum to other regions of space where frictional forces are negligible. Rotational motion is capable of enduring for incredibly long durations. A planet might spin for billions of years. A galaxy can revolve for as long as the universe has existed. No external force is required to sustain these movements. Inertia performs this function at more minute levels. This identical principle holds true within atoms. Electrons reside in configurations characterized by angular momentum. Their inherent spin and orbital movement dictate the manner in which atoms connect and how molecules are structured. These rotational states are capable of flipping or exchanging energy. Nevertheless, the overall angular momentum within the system is consistently preserved. The field of chemistry itself is governed by this principle, and the measurement of time also depends upon it. The most accurate timepieces ever constructed by humankind operate on the basis of atomic transitions. Electrons move between energy states, possessing precisely defined angular momentum. The accuracy of timekeeping relies on the consistency of spin. At greater magnitudes, planetary rotations establish days, orbital paths determine years, and galaxies mark cosmic eras through their gradual revolutions. Practically speaking, time is quantified by movement adhering to conservation principles. However, if angular momentum consistently remains conserved, what accounts for some systems rotating quickly while others hardly move? The explanation is found in their past. Each object retains a record of its previous interactions. A rapidly rotating neutron star achieves its speed due to collapsing from a significantly larger entity. A slowly rotating planet might be sluggish due to the loss of its rotational energy via collisions or tidal forces. The rotational pattern of a galaxy mirrors innumerable fusions and interactions spanning billions of years. Rotation isn't bestowed, it's gathered over time. This inherent historical aspect of spin provides the universe with its distinct character. No two systems are exactly alike. Each possesses a distinct rotational signature molded by its genesis and interactions. Nevertheless, despite this variety, the identical principle applies universally. Angular momentum is indifferent to an object's composition. This principle extends to cosmic dust, gases, stars, planets, light, and even space-time itself. Angular momentum can even be possessed by space. Gravitational waves, which are distortions in space-time generated by accelerating masses, possess the ability to carry rotational energy away from systems. As colossal objects revolve and coalesce, they release angular momentum into the cosmos as these waves. They delicately alter the equilibrium of movement throughout vast cosmic expanses. This uncovers a nuanced truth. Spin isn't merely an attribute of individual objects. Rather, it's a characteristic of entire systems. It's impossible to fully separate it. It inherently pertains to the connections between matter and space, and between objects and their environments. Rotation endures not due to an external compulsion, but because the cosmos maintains equilibrium with remarkable exactitude. For this reason, no single ultimate arbiter of spin exists. What exists is merely an accounting. When one thing decelerates, another accelerates. Each time rotation diminishes in one location, it resurfaces elsewhere. The cosmos consistently remembers these quantities. This meticulous record-keeping even encompasses time, given that time is affected by movement and movement is regulated by conservation laws. The progression of time acquires this equilibrium. Time accelerates in some areas and decelerates in others, yet its fundamental framework stays uniform. Viewed this way, spin functions as the universe's inherent gyroscope. It steadies movement, safeguards historical data, and guarantees ongoing existence. Lacking it, systems would rapidly disintegrate or become static. With its presence, intricacy endures. Nevertheless, notwithstanding this regularity, spin does not persist eternally uniformly across all locations. Although angular momentum is preserved on a universal scale, localized systems are capable of nearing a state of immobility. A planet might achieve tidal locking, perpetually presenting an identical side to its parent star. A star's rotation can decelerate as it expels material. Following mergers, a galaxy may forfeit its elegant spiral form, adopting a more spherical appearance. It grows more tranquil and less energetic. Rotational energy becomes diffused, distributed over vaster regions of space. This prompts a thought-provoking inquiry. If rotation influences time, and if rotation gradually dissipates, what will be the fate of time in the distant future? What transpires when movement becomes so widely dispersed that no object can effectively spin? This inquiry guides us to the frontiers of cosmology, a realm where galaxies drift away, stars dim, and the cosmos gradually loses its inherent motion. However, before we proceed down that route, a different enigma awaits our consideration. If the cosmos operates on equilibrium, and if the initial impetus for motion arose from symmetry disruption, what transpires when that symmetry is fractured once more on the grandest possible scale? The cosmos did not originate uniformly. Instead, it began with an imperfection, and this very flaw might be the fundamental reason for all existence. To grasp this, we must journey back even further, to the precise moment when flawless symmetry gave way and the universe opted for dynamism over stillness. Picture a cosmos in complete equilibrium, where no orientation is favored above any other, and no distinction exists between left and right, past and future, or specific locations. Within such a universe, absolutely nothing would ever transpire. Movement would lack any impetus to commence, formations would have no cause to materialize, and time itself would lack any reason to advance. Flawless symmetry is not potent, it is quiescent. The cosmos we occupy is decidedly not quiescent. Right from its inception, an inherent imbalance existed within its physical principles. Symmetry denotes that the fundamental principles of nature stay constant even when a system undergoes transformation. This includes inverting it, spinning it, interchanging particles, or altering its orientation. Symmetry possesses an inherent grace, and during the cosmos's initial moments, physical laws imply its near-total completeness. Almost, yet that solitary imperfection fundamentally reshaped existence. Within the initial fractions of a second, the cosmos existed in an inconceivably hot and dense state. At such energy levels, the distinctions we currently regard as foundational had not yet materialized. Forces presently distinct were once integrated. Particles functioned as manifestations of shared foundational fields. Space-time was intrinsically linked, undergoing swift expansion from an initial condition that was remarkably uniform. However, uniformity does not signify absolute sameness. Subtle quantum fluctuations, slight energy variations inherent to quantum fields, were evident right from the outset. Such fluctuations proved inescapable even within the lowest possible energy configuration. Quantum systems are incapable of absolute stillness. They constantly quiver and vary. Perfect homogeneity is disallowed by nature's principles. As the cosmos expanded, these minuscule divergences became elongated across immense expanses. Initial minute disturbances became ingrained within the very fabric of space. Certain areas ultimately became marginally denser than others. Some possessed slightly greater energy. Others exhibited minor directional preferences. These disparities were not predetermined, yet once expansion solidified them, their removal became impossible. This signifies the precise instant when symmetry genuinely fractured. Once the cosmos had cooled sufficiently, it experienced a succession of phase shifts. These were occurrences in which its foundational condition was altered, even as the underlying laws persisted without change. It bears resemblance to water solidifying into ice. The principles governing water's behavior do not undergo alteration. However, the system's inherent symmetry is indeed modified. Liquid water presents an identical appearance from any vantage point. Ice adopts a particular crystalline arrangement. The universe behaved similarly. As temperatures decreased, previously unified forces diverged. Novel distinctions emerged. Particles acquired mass, and fields settled into particular configurations. Every transition solidified disparities that had not previously existed. Upon each instance of symmetry breaking, new attributes manifested, and among these was direction. Direction serves as the genesis of movement once it is established. The process of collapse can no longer proceed in a perfectly straight line. Gravity exerts an inward pull on matter. Yet this action is not uniform. Matter converges from diverse directions. Accompanied by minute lateral movements, these very motions prevent a complete collapse. Rather, they give rise to rotation. Spin is not subsequently introduced. This is the inherent result of an imbalance operating under the force of gravity. Consequently, rotation is observed universally not because of an intentional design. Rather, it's due to the near impossibility of a perfectly symmetrical collapse once symmetry has been disrupted. The universe doesn't quietly draw inward, it spins as it consolidates. Furthermore, symmetry breaking clarifies the fundamental reason for matter's existence. Within the nascent universe, matter and antimatter were generated in nearly equivalent proportions. Per the established principles of physics, they should have completely annihilated, resulting only in radiation. Yet, this didn't happen, for reasons still being researched. A minuscule surplus of matter was present, roughly one additional particle for every billion pairs. That distinction was adequate when matter and antimatter annihilated. That excess persisted, forming all you observe today: galaxies, stars, planets. Your physical form is constructed from that remaining imbalance. Had symmetry been absolute, the universe would be solely filled with light. The identical principle holds true for motion. Perfect symmetry results in stasis, whereas broken symmetry brings about change. Even the temporal direction seems to arise from this initial disequilibrium. The core laws of physics largely permit processes to unfold both forwards and backwards in time. However, our perception of time is unidirectional. Effects invariably follow their causes, and systems develop, degrade, yet never spontaneously revert. This temporal directionality is intrinsically linked to entropy, the inherent inclination of systems to transition from organized states to disarray. Nevertheless, entropy's behavior is contingent upon initial conditions. The early cosmos originated in an exceptionally low entropy state, displaying considerable order despite its high temperature. This initial state constituted a further instance of broken symmetry, which permitted time to acquire its specific direction. Spin also contributes in a subtle way here. Spinning enables structures to endure far from equilibrium, retarding their collapse. It disperses energy, thereby extending the burning duration of stars, maintaining galactic structures for longer periods, and preserving planetary dynamism for extended times. Absent rotational motion, systems would accelerate their progression toward uniformity considerably more rapidly. With rotation, complexity is afforded the opportunity to manifest. Even at the most minute scales, nature exhibits a preference for certain subatomic processes that differentiate between left and right. Specific particles consistently rotate in an identical direction relative to their movement. These breaches of symmetry are intrinsically embedded within the weak interaction itself. At its most foundational stratum, nature is not perfectly ambidextrous. This inherent bias resonates through higher levels. The indispensable molecules of life exhibit chirality. Biological chemistry invariably favors one specific orientation over its mirror image. This selection is not solely dictated by chemical principles. Its origins likely trace back to physical asymmetries present long before life existed, possibly even to the identical fundamental violations of symmetry encoded in the universe's earliest moments. Across scales, from particle spin to molecular architecture and from planetary rotation to galactic movement, the recurring theme is evident. Symmetry is disrupted, direction emerges, and movement endures. The cosmos's inception was not a direct consequence of symmetry breaking, but the universe we recognize, the one with temporal structure and motion, could only exist because symmetry did not remain intact. Absolute, unbroken perfection would have yielded sterility, disparity generated potential, and once disequilibrium was present, the cosmos was unable to remain static. Movement ensued organically, rotation grew inevitable, and time acquired its orientation. Material substances discovered methods to self-organize rather than disintegrate. This explains why movement appears so profoundly integrated into reality. It is not merely an incidental occurrence superimposed upon existence. It represents the cosmos's reaction to its own imperfection. Each orbit, every rotation, and every cycle serves as a testament to that initial divergence from uniformity. As you observe the celestial sphere rotating above, and as you perceive the gentle cadence of day transitioning into night and night reverting to day, you are witnessing the most enduring outcome of that initial disruption of equilibrium. It is not chaos, but rather continuity, not disorder, but instead structure. Originating from disparity, the cosmos rotates because it was incapable of maintaining absolute equality in every aspect. And through this rotation, it acquired temporal structure and the environment for life to perceive its ongoing motion. Should you appreciate this video, please remember to give it a like and subscribe. Your support significantly impacts us and contributes to the channel's expansion.